Okay, thank you, Seth. Today I'll be talking about quantum Hall effect, but I want to talk about fractional quantum Hall effect. Mm, I mean, this is a very wide topic, and there are tons of very good reviews and lecture notes on this topic, such as the lecture notes by Stephen Gerving and the chapters in this book by Gerving and Kuhn and Yang. There are also lecture notes by David Tong, which are very good. So today I'll be this is my outline. So I'll be talking about some basic stuffs of fractional quantum Hall and effective field theory, which is Chern-Simons theory. And if I have time, I'll talk about dualities to make contact with a previous journal club topic by Robert. So let's get started. So this is the famous Hall measurement. So as we can see, there are some plateaus in Hall conductance at integer fillings, which are called integer quantum Hall effect, and also as some fractional fillings. So we are all familiar with integer quantum Hall. Basically, it can be explained by fully filled Landau levels of 2D electrons, 2D electron gas and magnetic field, and plus some disorder, which caused the plateau. So for fractional filling, it's a little bit weird, because if we consider partially filled Landau level, it seems there's no, I mean, if we do not include any electron-electron interaction, there's no way we can get an incompressible state. So that means Coulomb interaction must be very crucial in this fractional quantum Hall context. So for the rest of my talk, I'll assume this hierarchy of energy scales, which is disorder much less than the Coulomb interaction, much less than the Landau level splitting. That will allow us to work with the projected states living in, say, lowest Landau level or a few Landau levels, and ignore the Landau level mixings. So with that, the Hamiltonian we're considering is basically contains two terms. One is some electron gas coupled to a external magnetic field. We all know how to solve that. It will give us Landau levels. The other one is a Coulomb interaction. We are taught to do perturbation theory during our in the grad courses, but notice that if we have a fractional filling, the ground state degeneracy of the ground state of H0, their degeneracy is huge. So it's a very hard problem to do a degenerate perturbation. So Laughlin made a very bold move. He's like, how about I just guess the ground state wave function directly? I mean, after all, that's what we want. So yeah, so let me introduce the guess wave function, which is the Laughlin wave function. And yeah, let me just motivate let me just motivate this sorry. Yeah, let me just give you some motivation. So for if we consider a single particle state, the wave and assuming symmetric gauge the wave function for lowest lambda level is just some holomorphic function times an exponential decay component. So the power here, m, is actually it actually labels angular momentum, and this wave function actually localized on a ring of radius, which is square root of proportional to square root of m and times the magnetic length. So with the interaction between two particles, we can consider the ground state wave function of the two particle states. Luckily, if we decompose the coordinates into a relative displacement and solving the Hamiltonian with this interaction, we can see the two particle state is actually in this form. So in general, it's I mean, for n equals 2 particles, it's impossible to solve this Hamiltonian and write down the ground state wave function, but we know that it should be of this generic form with a holomorphic function that's that depends on C1 to Cn if we have n particles, and they should be an anti-symmetric because we're considering fermionic systems. So motivated by this two particle function, this C1 minus C2 to the n seem to be very cute. So I mean, we can so Laughlin proposed this kind of wave function for a filling fraction 1 over m fractional quantum Hall states. Okay, so let's just forget about the Hamiltonian for 1 second and study this wave function directly. So indeed, if m is odd, this wave function describes fermionic systems. If m is even, that's a wave function for bosonic system. But how about the filling? How do we know the filling fraction is 1 over m? So notice that the highest angular momentum for, say, C1 is m times n minus 1, where n is the total particle number. As we said before, this power is actually related to the ring of the radius where the wave function has a maximum probability distribution, and this maximum radius can be thought of as a radius for the quantum Hall droplet. It's proportional to as thermodynamic limit when n goes to infinity, we throw out this -1, and this is the maximum radius for the Hall droplet. And there are and we have n particles in total, so we can compute the filling fraction of it. It will simply give us 1 over m. So this is nice, but okay. But if we want to do anything, if we want to compute any physical observables using this wave function, it seems a little bit hard. because it's a many-body wave function with thermodynamic like with many numbers of arguments. So say if we want to compute the charge density at point C, then we need to compute something like this, where P is the probability distribution. So, but this guy actually looks a little bit familiar if we rewrite this probability distribution as some kind of fake Boltzmann distribution with some fake temperature. Okay, then the fake potential U can be written in terms of these guys. Yeah, this looks a little bit, kind of looks bizarre, but if you're familiar with a 2D Coulomb gas, then this will look very familiar to you, because actually this log term describes a 2D Coulomb interaction between 2 point charges, and this term actually describes a point charge with charge M interacting with a uniform charged background with a uniform charge background. So note that this M is so in this fake Boltzmann distribution point of view, this M looks like a fake charge of the particles, and they interact with a uniform charge background. So so in order to have the lowest Coulomb energy, they want to neutralize the background. That means the charge density wants to be of this form. So that the plasma looks neutral on average, and yeah, and we can try, and people try to plot some this is snapshot of this kind of distribution. So if it's a Poisson, this uncorrelated one, then it's on the left. But for this plasma, you can see that it's kind of uniform. So I mean, this plasma analogy actually I mean, from the point of view of feeling fractional, it actually doesn't tell us anything new. But it does tell us something new. But what's new in this plasma analogy is that we get almost uniform charge distribution, which seems which is not very obvious from the form of the Laughlin's wave function. Because from this wave function, you might think that C equals 0 is some special point, but it's actually not. So far we've only talked about the ground state. The ground
state. So can I just sorry, interrupt with a question. So can you then comment on like the gauge dependence of all of this stuff that we've been doing? Is the claim that even though we have this, like, even though it looks like everything is living in a droplet or something, the fact that we get this uniform density means that that we're extracting correctly gauge invariant quantities from this? Like this whole formulation depended on choosing a particular gauge for the potential, right?
Yeah. So here we choose a symmetric gauge.
Right. But you know, if I choose some different, Well, yeah. So if I choose a different gauge, like B is just equal to, or A is just has like one non-zero component or something, right? Then
Yeah.
certainly, and nothing is going to look like there's going to be no angular momentum, no droplets or anything. So like, to what extent is the, yeah, where so this
Okay.
claim about the density of this wave function is something, even though the wave function itself is not gauge invariant, right? What is,
Yeah.
what are we?
Okay. So yeah, yeah, but here we are actually computing a gauge invariant quantity, right? It's the charge distribution.
Mm-hmm.
So it doesn't depend on gauge choice. I mean, I think the beauty here is just that I can choose the convenient gauge, such that I can see the results in a very easy way.
Mm-hmm.
Yeah, instead of say choose a Landau gauge, where I don't know how to write this wave function will be a little bit complicated.
Mm-hmm. Wait, sorry, this is just dumb, but can you remind me why this is gauge
Why
dependent
this?
here?
You're saying why?
Why
Sorry.
the expectation value of n in that particular psi
Mm-hmm.
is independent of the formula, because our gauge transformations aren't like acting as phases on psi or anything.
Uh,
I'm just
so
thinking to myself that the form for the wave functions would look like completely different
yeah,
in
in a different gauge, right?
yeah.
Yeah, but n here is just some. I mean, it's just a delta function.
Mm-hmm.
I mean, this is a physical observable. It shouldn't depend on any gauge choice.
Mm-hmm.
Yeah, and this plasma analogy just it's I mean, it's an intuitive way to see how this to I mean to have an intuition for a property of the wave function. I mean, it's not actually there's not actually a temperature or something.
Right. Okay. So you even though the whole wave function is localized in a exponentially localized in a droplet, the claim is that the density is still uniform.
Yeah, the density is almost uniform.
But isn't that weird that since psi only has like is exponentially is only supported on like a compact region? Okay. Well, whatever. Okay, I guess it's just surprising, but that's
Yeah, I agree, that's very counterintuitive. Yeah, but if you think of it in this plasma way, it also seems a natural conclusion.
mm-hmm.
I mean, it's not. I mean, it's not at all obvious from the form of the wave function. I
Mm-hmm.
agree. Yeah, and I also need to be careful about this plasma analogy, because here it's actually a finite temperature, and yeah, so one may worry about whether this guy, whether these charge will froze, stuff like that. Yeah,
Mm-hmm.
but if one did the people did numeric on these stuff and found that for m say less than 70 or something, this uniform distribution picture actually works pretty well. Yeah. Okay.
Oh, go ahead.
Sorry, any other questions?
No, I was just saying, maybe I'm being stupid here, but it being localized to like to a ring that was with the wave function, right? So if you were looking for some place for gauge dependence to rear its ugly head, I mean, that's probably where I would look. Once you look at the charge density here, that's where you applying the plasma analogy, right?
Yeah.
Right. So the local, I would trust the plasma analogy more than the wave function being localized on that ring. At least when I'm thinking about gauge dependence. Anyway, sorry, unnecessary comment.
Yeah. Sorry. Right. Here in the previous slide, I just gave a very hand wavy argument, and it's actually only for one single particle. I mean, after all, we're dealing with
this
this
psi is
many
still
body
like,
stuff.
if I send magnitude of z to be very, very large in the thermodynamic limit or something, it still looks like psi goes to 0. It's too fast for it to be able to provide a uniform density. Well, anyway, okay.
Okay, yeah. Right. So far we've only talked about ground state. So let's consider what kind of excitations we can have. So so we'll be talking about charge excitations first. So that means we are talking about quasi-holes and quasi-particles. So I mean, so in the spirit of guessing wave function, we can just guess the quasi-hole wave function. So yeah. So people propose this guy to be a wave function of one hole at position eta. So let's see if this is I mean if this makes sense. So if I have one hole at position eta, I mean this wave function does have vanishing amplitude when z approaching eta. So it looks fine. And we can also try to put m holes at position eta 1 to eta m. So yeah, this seems to be legitimate. So let's see how about the charge of a single quasi-hole? Surprisingly, the charge is actually 1 over m. Okay, so one hand waving argument is that if I put m quasi-hole together and they all at position eta, then this guy will just be c minus eta to the power of m. And it looks like the Laughlin wave function we get before, but with eta fixed instead of varying. So that means we fix one electron in our system. So yeah, so that means if we put m hole together, we get an electron. Yeah, that means the quasi-hole actually has a charge 1 over m. Yeah, this may not look very convincing, but again, we can use the plasma analogy we just learned and write the fake potential, which looks like this guy. So for this one hole wave function, we get a additional term, which looks like this. It's a defect with charge 1. So, right, as we said before, the whole purpose of this plasma is want to be neutral. So if I have a defect with charge 1, then all the particles will want to screen this fake charge, but notice that in this plasma analogy, the charge of the particle is actually m. So I only need 1/m of the charge density. So, but the particle actually has physical charge E. So that means the charge of the quasi-hole is 1/m times the physical charge. So we can also consider a quasi-particle wave function. One way to consider a quasi-particle wave function is that, so notice that in the quasi-hole wave function, we want to raise the power of angular momentum, such that the quantum Hall droplet will be larger, but we still have n particles, so it will be so effectively it will introduce Hall. If we want to introduce particle, that means we want to lower the angular momentum. So one way to do that is, of course, we can divide this guy by itself once, but then it's problematic because it will introduce a singularity. But we can also multiply this guy by c bar. That will also lower the angular momentum, but c bar is not a legitimate lowest Landau level wave function. So people did some projection to get this form of quasi-particle wave function. I mean, it looks very hard to deal with, and and indeed, I'm not going to talk about this wave function anymore. I'll be dealing with the quasi-hole wave functions. So I told you that the charge of a single quasi-hole is 1/m, but how about the quantum statistics of these guys? So that means if I exchange two quasi-holes, what will I get? So we can compute this exchange angle by considering the Berry curvature of this wave function containing m holes, and just move one hole around another one to get the statistic angle. But a caveat is that in order to compute the Berry curvature, we need to work with a normalized version of this guy, which is this one, where C is just this partition function we get in the plasma analogy. And right. Again, we want to see what a plasma analogy can teach us. So this whole system looks like we have some kind of defects, and also a uniform background charge, and a Coulomb interaction between particles. There's a Coulomb interaction between particles, Coulomb interaction between particle and defects, and a Coulomb interaction between particle and charged background. But that's not the whole Coulomb interaction. If we're considering a system with those charge defects, we are missing two terms. One term is the Coulomb interaction between the defects themselves. The other one is the Coulomb interaction between defects and the charged background. So if we add those two terms, it looks like this corrected potential actually describes the interaction, the whole Coulomb and interaction energy containing these defects. So yeah, so as I said before, the whole purpose of the plasma is that they want to be neutral. So yes, so if the plasma, if the total stuff is neutral, then it doesn't matter where I put those defects. They will be screened. So with that means actually, if we consider this corrected potential, if we replace this corrected potential, replace the original potential by the corrected one, the resulting fake partition function will it doesn't depend on the position of eta. So that means the Berry curvature of this guy actually vanishes. So we only need to consider the effect of these two underlying terms to the Berry curvature. Yeah, this is much easier to deal with because we don't need to integrate over those z's. And indeed, if we compute the holomorphic Berry curvature of this guy, we get some factor like this. So if we rotate, say, one quasi-hole around the other, or rotate, say, eta 1 around eta 2, we'll get a phase factor that's proportional to 2 pi over m. Note that the statistic angle is actually rotate 180 degrees, not 2 pi. So the statistic angle is 1 over m. So yeah. Okay. So far we've been dealing with charged excitation. I also want to mention in bypass in those systems there's also neutral excitations which are phonon-like. It comes from density fluctuations. It's similar to what happens in superfluid helium-4. But the major difference between the superfluid and the quantum Hall fluid is that the phonon distribution is the phonon is gapless in superfluid, but it's gapped in a quantum Hall system. Because in superfluid there's a ghost tone mode, but this quantum Hall fluid actually it doesn't have any ghost tone mode, etc. And analogously, there's also a Rotom minimum in this in the quantum Hall fluid, which people call magneto Rotom minimum. Yeah, if I have time, I can talk about how to get this more. But yeah, let me just skip the neutral excitations. Okay, so far we talked about Laughlin wave function and the plasma analogy to it. But actually, we can view a Laughlin wave function from another point of view, which is the point of view of composite fermion. How does this work? So the Laughlin wave function is this guy, and if we decompose this factor to m+1 power of m+1 and power and 1, this second guy looks like and times this exponential coefficient, it just looks like a fully filled lowest Landau level wave function. So and but I mean, intuitively, this Laughlin wave function just looks like we attach to this Z another vortex of power m-1. So this motivates Jane to write down some states like this guy, where this psi new star is a wave function of a fully filled new star's lambda level. In the case of Laughlin wave function, this new star is 1, and attached to it some m-1 flux, and after that we need to project the whole thing back to the lowest lambda level. Because in this fully filled, if new star is not 1, there will be some anti-holomorphic part that's not allowed for a wave function in lowest lambda level. Okay, so let's see what this composite for. By the way, we call the fermion in this new star lambda level composite fermion. So let's see what this composite fermion picture can teach us. So, yeah. So so first of all, this new star, the fermion inside this lambda level wave function, it should feel a different magnetic field because we attach vortex to it to get back the original one. So yeah, so actually the magnetic field felt by the composite fermion as the original magnetic field minus the m+1, which is the strength of the vortex, times the like the density of those gas. So and also the for each composite fermion we attach m-1 vortex. So the particle density of the composite fermion and the particle density of the original guy should be the same. That allows us to determine a new filling fraction, which is this new star and related to the original one. So yeah, so the relationship between the new star and new looks like this guy. We can pick any new as long as it's an integer. So this gives and m is also integer. So this gives a whole sequence of wave functions, which are called which is called Jane sequence. So we can look at some examples. For example, if we attach two, say m equals 3, that means we attach 2 vortex to a fully filled fully filled first lambda level new star equals 1, a 0th lambda level actually. So we'll get a nu equals 1/3, which is the which indeed gives the right filling factor, because remember for the Laughlin state, if we have the filling fraction 1/m, and this can also be reproduced by considering composite fermion. Yeah, actually there's a very interesting example to it, is if we consider m equals 2 and this b star equals 0, that will give a half-filled lambda level. But notice that this wave function is actually not correct for that half-filled lambda level, because the magnetic field of the magnetic field that's filled by the composite fermion is actually 0. So the composite fermion can form Fermi liquid. So we can So instead of this Jane state, we can write nu equals half state like this guy, where this determinant is just a wave function of a Fermi liquid.
Can I ask another question? So
Sure.
sorry, can you remind me why the lowest Landau level has no z bars? I forgot why this.
Oh, it just comes from the symmetric gauge. If you choose a symmetric gauge, then the lowest Landau level wave function will always be a holomorphic function times some coefficient. Here here I didn't include any the exponential factors.
Mm-hmm. But okay, so that follows from the Hamiltonian or something?
That boils down to so first of all, the energy scale in our problem is the Coulomb energy much less than the Landau level splitting. So so we can just consider the projected Hilbert space spanned by the wave function of the lowest Landau level of the non-interacting Hamiltonian.
Yeah, okay. And so the claim is that if I were to write a z bar and psi or something, what would that be doing?
If you do a projection to the lowest Landau level, it will give you something like partial z.
Okay, so the rule for implementing this PLLL thing, right? If I have some z bars in psi, I try to replace them with derivatives as you did earlier when you were describing the quasi-particle wave function.
Yeah. With with derivatives on this factor.
Okay, I see.
Yeah, any other questions? Okay, so this Jane sequence is very nice, but it only gives rise to a certain kind of the filling fraction, which is with odd denominator. So in the spirit of guessing ground state wave function, we can try to do more than a Laughlin wave function. So yeah, that is so Moore and Reed propose this kind of states. So this I ignore the exponential factor. So this Moore Reed state is very it has a very peculiar form with a Pfaffian in front of it. So so it's also called Pfaffian state. So the Pfaffian is something like a square root of determinant, which is defined by this expression. So yeah, so let's first look at a single example. If we have n equals 4, so the Pfaffian of this guy with 4 particles can be written as something here. So basically, we just partition 4 particles in terms of 2 particles and 2 particles, and exchange indices with some sign of the permutation. sorry. Yeah. So this Farfian coefficient times this guy, yeah, it actually doesn't have any divergence when Zi approaches Cj. So this is very good, and also because this Farfian is naturally anti-symmetric, so this Maury state is for bosonic system when M is odd, and for fermionic system when M is even. So that's a difference between this guy and the Laughlin wave function. So interestingly, actually for M equals 2, this describes a p-wave superconductor for the composite fermion at half at nu equals 1/2. So we can also consider the quasi-holes for this wave function. So naively, we will just include this prefactor in front of the Farfian for one quasi-hole. But why not we do this? We can write something. We can mess up with this Farfian coefficient and put this coefficient inside the Farfian stuff, and you can see that when eta 1 approaching eta 2, this guy is proportional to this guy. Yeah, so that means we actually have this putative half-hole actually putative quasi-hole actually splits into two quasi-holes. Yeah, so that's very interesting, and we can include more quasi-holes in terms of the coefficients on the numerator of this Farfian. And so now we want to count how many states there are if we have 2n quasi-holes. So naively, we divide 2n quasi-holes into 2 piles. So naively, we will have this much of this many states, but actually those Farfian are not linear independent. So the linear independent ones are only 2 to the n minus 1, much smaller compared to the naive counting. Yeah, so why this happens? So as I mentioned before, actually this M equals 2 is a p-wave superconductor for composite fermion. So these quasi-holes are actually vortex in a p-wave superconductor. So if we compute the bound state of the vortex in p-wave superconductor, we will find that it's actually a Majorana fermion. So that if we have some Majorana fermions, so I mean we'll need 2 of them to form a complex fermion, and such that we can have 2 states, such that we can have this complex fermion occupied or not occupied that spans a 2-dimensional Hilbert space. So that's why we get this bizarre number of linear independent states. And those yeah, and if you are familiar with p-wave superconductor, this Farfian coefficient is actually a wave function of that superconductor. Yeah, and these these vortex, so these quasi-holes of the Maury states at m equals 2 we'll find later. I probably will not have time to talk about it. It's actually called Ising anyons. So yeah, so so far those wave function approaches looks good, but when we are dealing with states like Maury states, this wave function looks very complicated, and it's not at all obvious how we can obtain the statistics of the quasi-holes, right? If we want to compute, say, just the space, just the space of the Hilbert space of the quasi-holes, it will take a lot of effort to try to analyze those fermion coefficients. So an alternative way of dealing with fractional quantum Hall is we sort of take a coarse-grained approach and think of what kind of effective field theory what's the effective field theory for quantum Hall. So by effective field theory, I just mean since the quantum Hall states are gapped, we can just integrate out those matter fields and get some effective action with a background gauge field, where the gauge field is a probing field. It's not the original magnetic field that caused the quantum Hall state is not included in this big A. So from a general consideration of a reasonable field theory, we require the theory to be gauge invariant, and we also want it to be local, and we're also dealing with probing fields, so we want an effective theory at long wavelengths and relatively small gauge fields. So there are not many terms we can write down, and we can write down them order by order because we're considering this limit. So the leading order term is it's called the Chern-Simons term, which looks like this guy, and the next order is the Maxwell term. So yeah, so the Chern-Simons term plus Maxwell term actually gives a gapped photon spectrum. So it's good because we want to consider gapped theories. Also, if we compute the current of this probing field, it actually gives a Hall. It actually has a Hall coefficient, which is also nice. But one puzzle is that this Chern-Simons theory seems to be gauge invariant. So I mean, there seems to be no constraint of this Hall coefficient. So how does it how can we relate it to integer quantum Hall? So actually, if we consider a large gauge transformation, we'll find that this K must be integer. So by large gauge transformation, one gauge transformation one can consider is that we can put this system, we can turn on the finite temperature, meaning the we can do a weak rotation to okay, so to consider a finite temperature configuration, and make this make the space compact, consider a sphere, and we insert a magnetic monopole to it, consider the whole path integral. Yeah, and we can for this so the gauge invariant actually requires this partition function to be single valued, but this effective action can have some phase factor. After considering that, taking that into account, we'll find that k must be an integer. But as we talked before, we can have Laughlin states, which I mean the whole response doesn't need to be integer. So what happened here? So let's put this aside and just consider another theory with emergent gauge field coupled to the probing gauge field. And since now we know this Chern-Simons term is actually gauge invariant, we can, introduce a Chern-Simons term for the emergent gauge field and couple and have a mutual Chern-Simons term between the probing field and the emergent field. So then the current of this probing field is given by this guy, and automatically the current is conserved. But if we consider the equation of motion for the little a field, we'll find that this little a field is actually 1 over m to the big A field, with some plus some gauge stuff. That will give us a whole conductance which is 1 over m. And furthermore, if we integrate out this little a field, we'll get a 1 over m coefficient in front of the Chern-Simons term. So that seems that conflicts with the observation we just had. That mean right? I just told you this the gauge invariance require this coefficient to be an integer. So what's wrong? So actually there's there's nothing wrong about this guy. The problem is with the Dirac quantization condition. Note that in the large gauge transformation I told you before, we insert a magnetic monopole which has a strength 1 that's determined by Dirac quantization. But here, for this, I actually require the Dirac quantization condition for the little a field, not for the big A field. That's why we get this 1 over m coefficient. So with that we can see this if we don't impose any Dirac quantization condition, the coefficient is actually meaningless. We have to specify what we call charge 1 to make those coefficients meaningful. Yeah, that's a caveat of dealing with Chern-Simons theories. Wait, oh, okay. So from the Chern-Simons theory, we can also calculate the quasi-holes and quasi-particles. We consider quasi-holes and quasi-particles and their statistics. Yeah, that's I think that's if you take Xiaogang's class, I think this is one of the homework problems. Yeah, basically starting from the effective action we had before and add some charge density to it. So yeah. And if we consider the equation of motion for the little a field, and turn off the probing field big A for a moment, we'll see that actually this charge of the charge of this electric charge is attached with some magnetic flux of little a. So people often call this flux attachment. And if we plug what we get from the equation of motion of little a field back into the definition of the current, we'll find we get an a fractional charge. So yeah, so we can also consider the statistic angle of two quasi-particles by solving the equation of motion of little a field and computing the AB phase of by considering the AB phase of rotating one quasi-hole around another. In the end, you'll get the same result as we talked before. Okay, this emergent gauge field, considering these emergent gauge field is looks like a very promising move. So why not having more of them? So we can have more emergent gauge fields. And in general, the effective action will be like this guy. So we have a Chern-Simons term between the emergent gauge fields and the mutual Chern-Simons term between the emergent gauge fields and the probing field. And the coefficient here is a matrix. People call this K matrix. So we can also consider the hole conductance, the charge, the statistic angle. You can work out those by yourselves, I think. Yeah, and they all have this very beautiful formulas. Also note that different K matrix and this T vector doesn't necessarily give us different states. So there's actually an equivalence relation. Yeah. So if we but note that we also want to impose the Dirac quantization condition. So this equivalence relation is given by this S matrix, which is an element of the SLNC matrices. So to make contact with what people talked before, like toric code. So actually this K matrix can describe many other topological orders, for example, such as toric code. Although I mean, we can forget about this coupling to the probing field for now, but for this K matrix, the K matrix for toric code is simply this guy. So we can check the statistic angle and find that E particle and M particle actually charged under these emergent gauge field with a charge 1, 0 and a charge 0, 1. Okay, so we talk so I tell you that this effective Hamiltonian can describe quantum Hall states, but we can also put the matter field back and make the so this effective action is integrate over the matter field. So we can also put the matter field back to see what happens. Yeah, and actually this so yeah, so I actually want to talk about the particle vortex duality. In the particle vortex duality, on one side we have the SY model. On the other side we have the Abelian Higgs model. So we have a global U1 symmetry on both sides. And if we gauge that global U1 symmetry with a dynamical gauge field little a, and now we know that we can have Chern-Simons term as some gauge invariant terms. We can just put the Chern-Simons term here and here. So notice that in this theory A, if we consider the current to the, so if we consider the current is actually given by this guy, it looks a little bit like it looks pretty much like the current we have. Okay, the current we have here. Yeah, so that means in this description of this XY model, if we couple it to, we can also couple it to a probing field, which I didn't write down. So yeah, so then this vortex is actually an electron, and the phi quanta actually gives the quasi-particle. But we can also see that in the dual description, these two guys get reversed.
So Dan, let's see. I think we're a little over time.
Sorry.
No, that's okay. But yeah, so just like maybe in 5 minutes. I don't know.
Oh yeah, sure. So yeah, so we can consider the phase diagram of both sides and work out so if say yeah, and match the phase diagram of both of the two sides. Also I mean, in this language of particle vortex duality, this phi field is actually has an anti-particle, and people also people, in order, if you want to get a Ginsburg-Landau theory plus the Chern-Simons, you need to consider actions like this guy. So where notice that we replace here this phi is relativistic, and here this little phi is actually non-relativistic, and we put a chemical potential to it. Yeah, so I mean, at near critical point of this superfluid insulator transition, these two theories should be the same. Yeah, and we can also consider half-fill Landau level and couple it, yeah, and do the duality. But yeah, but it's it will be a very long story for this half-fill Landau level. So I'll stop here.
Thank you. Yeah, so I had one question.
Sure.
When you wrote down the Moore Reed state, you said for m equals 2, it's a p wave superconductor.
Yeah.
And so I was wondering if there's any physical way to understand this. Like, is there some sort of instability to pairing, or is it just like we're writing down this state and it is the description of a p wave superconductor?
Yeah. So the instability question really depends on the Hamiltonian, right?
Right.
So yeah, but here I just propose some kind of I just propose a wave function for this state. I don't
Got
have
it.
any. Yeah, it's not a statement of the instability.
Got it. Okay, thank you.
Yeah, I have a question. So, you were talking about how the Chern-Simons term plus a Maxwell term leads to a gap for a gauge field, right? And
Yeah.
yeah, you said this is like what we want, sort of. But I don't know, it's kind of surprising, right? You couple a gauge field to a bunch of gap stuff, and then somehow that gap stuff manages to produce a gap in the gauge field itself too, right? So why did we expect the response theory to have a gap?
Oh, I mean, I said that based on this, based on that, we want to get effective field theory for quantum Hall states, right? So we want to gap. So we want it to be gapped.
Well, let me think. So the matter is gapped, right? But so am I correct in imagining that capital A should be thought of as like the electromagnetic field minus the magnetic field that's causing the quantum Hall effect, or is capital A something different?
Right.
Okay, but like if I were to just couple A to a massive field, right? Then then coupling A to so if I had like, you know, Maxwell for A plus A coupled to massive thing, right? Then A would definitely not be gapped, right? I would just ignore the coupling to the massive thing, right? And so
Yeah.
here, if I don't add any A, I have a bunch of gapped matter, right? But then the claim is that I can couple A to this gapped matter, right? And it'll produce this quantum Hall and then lead to a gap in the A, which is kind of interesting.
Yeah, it's I mean, in this one way to think of it is in terms of this, in terms of the HLR theory, right? It's like yeah, it's similar to something like this. So
yeah, you have to you want to be coupling A to like a Higgs field or something, right? But
yeah,
I guess that's pretty inobvious that this is what's going on in quantum Hall, right? Okay, maybe you're saying that using particle vortex duality is the best way to understand this.
Yeah, I think that's one good stuff about particle vortex duality.
Okay, and then so the other question is then, I mean, yeah, you were talking about the Dirac quantization condition being important, right?
Yeah.
So, but of course, if A is supposed to, capital A is supposed to be like the physical electromagnetic field minus the magnetic field part, then, I mean, in like a real, maybe this is too pedantic, but like in a real sample, capital A should still have its quantization condition fixed, as in a normal charge one field, right?
Yeah.
Like if it's the physical electromagnetic field, right? So are we just saying that it's impossible to consider like a scenario where you only have one source, you only have like a 1 mth flux or something, because like there are no field configurations where you can create a 1 mth charge in reality. So that's why it's
okay, you're saying so.
And also this equation of motion is equating the field strengths, not the gauge fields themselves, right?
Yeah. So there should be plus something. Yeah, I
Okay.
didn't write it down. Yeah. This is the equation of field strength. Right. So yeah. So back to the question.
But
so
like the field
here,
strength doesn't care about this holonomy part, right? If I just say the two field strengths have to be equal, then why do I say A?
Right. Yeah, but at the end of the day, you get something, that's so the first round doesn't care about this Dirac quantization, but at the end of the day, we want the effective action we want gauge invariant theory, right? So I mean, it seems that by putting non-integer in front of the Chern-Simons term, the theory might not be gauge invariant.
Well, yeah, and I would say that that's true because the equation of motion you used was not the real equation of motion.
What do you mean?
If you're using the equation, I agree you can use the equation of motion to set the field strengths equal to each other,
Yeah.
right? But how do you know that? It seems like you get some. I mean, it seems naively that you get something that doesn't make sense if you also set the gauge fields to be related by the factor of 1/m, right?
Yeah, that's true.
So I would have thought that we ran into a problem because we pretended like the equation of motion was for the gauge fields instead of the field strengths, right? But then you're saying that there's actually no problem in that setting the field strengths like this to be related in this way actually makes sense, right?
Yeah, it actually makes sense. I mean, locally it doesn't care. The field strength doesn't care about this monopole stuff. I mean, this is a legitimate equation.
But the direct quantization for capital A should be the regular thing, right?
The Dirac quantization for capital A.
Right. Like, so this S effective with the 1/m would make sense if I could only consider magnetic fluxes of strength M for A, right? Capital A.
Yeah, right. Yeah.
But capital A is the physical electromagnetic field, so I can definitely consider a 2π flux for capital A, right?
Yeah, you can definitely consider a 2π flux for capital A, but yeah.
But then isn't there indeed something wrong with that?
Let's see. Okay, by considering yeah, I know. So you're saying that the Dirac quantization condition by capital A should always given by, by the original one because the fundamental electric charge is always E.
Yeah.
It's not E over M.
Right.
Right. But here we're actually we're actually considering a quasi-particle in this system. Well, by quasi-particle, I mean we can have M. If we consider inject an electron to the system, it will just split to M quasi-particles, and then they can move arbitrarily far from each other.
Yeah. So can I just say that this is equivalent to just pretending like I can consider configurations where there's only one quasi-particle?
Yeah.
Even though that's not gauge invariant under the little a.
That's gauge invariant under little a. That will cause this term to be not gauge invariant.
Okay, maybe I'll just ponder this for a bit. Thanks.
Cool. Any last questions?
Oh yeah, and so you kind of said this, but the Pfaffian, right? So the only thing I know about the Pfaffian is that it's a partition function. The partition function for Majorana fermions is a Pfaffian, right? So what is the kind of, I guess you're telling me the answer here on the slide, but like if I had a partition function where the like action for the Majorana fermions had this like zi minus dj thing, then that and then I integrated out the Majorana fermions, I produced this Pfaffian. So is there some physical understanding for this as coming from this Pfaffian as coming from the Majorana fermions in this way?
By physical, I think by physical understanding, maybe you can think of it in terms of composite fermion. Yeah. I mean, in terms of composite fermion, this is a p-wave superconductor for this composite fermion, and I think you can get this state by starting from the composite fermion Fermi liquid.
Yeah. Oh, okay, yeah. So it's just like Slater anti-symmetrizing, but for real fermions.
Yeah.
Okay, thank you.
Sure.
Thank you. It was a great talk.
Thank you for listening.
Yeah, thank you. All right. I hope everyone has a great Thanksgiving break, and I will see you in 2 weeks when we hear from Jiwon about DMRG.
Yay.
Cool.
Okay, thank you, Dan.
Thanks, Dan.
Thank you again.
Listening.